Hi there and welcome. In today's video, we're going to be going over a practice test that covers 2D motion. So this is the second practice test for test number 1 that covers unit 1. Starting with number 1, it reads, an object is at rest. 3 forces are exerted on the object. One force is directed 10 newtons due south, and another is directed 10 due east. Which of the following forces, when added to the other two, would make the total force be equal to 0? Now, you might read this question and think to yourself, we've not talked about forces at all. I don't know what this is about. Well, remember that a force is a vector quantity. And at the very beginning of the school year, when we give examples of the different types of vector quantities we're going to be talking about in physics, forces are one of those. So the main point from our beginning discussions was that you could describe any vector using arrows. So it doesn't matter if these are displacements, velocities, accelerations, or forces in this case, we could model it as just an arrow. So I have 10 south, and then I drew 10 east, and it wants me to know which force would be required to make the total force be 0. And so in essence, that's really talking about the vector sum. So this is just an application of the idea of a vector sum. And if I want this vector sum to be 0, when I add up all my forces, or when I add up all my vectors, it needs to return to the origin, to the very beginning. So I need an arrow that points in this direction. And so if I treat my tail as the origin, I'm going to find this as east, south, west, and north. It'll be right between north and west, so it's going to be one of these two answer choices. Therefore, I can remove C and D from the possibilities. Now, the only difference between A and B is 10 square root 2 and 10 square root 3. These refer to magnitudes. This is a direction. I can find the magnitude of this vector with legs of length 10 and 10 by just using the Pythagorean theorem. So I'm going to call the hypotenuse C. So c squared is going to be a squared plus b squared. To find c, I'm going to take the square root of both sides. So I'm going to find the square root of 10 squared plus 10 squared, which would be the square root of 200. I can find the factors of 200. Namely, I can do 25 and 8. 25 is a perfect square, so it's going to be 5 times 5. So it's going to be times 5. And then the 5s can't factor anymore. I'm going to get 2 and 4. And this 4 is going to be 2 and 2. So I can create a pair of 2s, which is going to be a 2. What's left over is this 2. And because it does not have a pair, it belongs back in the square root. So 200 can be rewritten as 5 times 2 is 10, square root of 2. Letter A would be my answer choice here. Tim Tebow throws a baseball that travels a parabolic path as shown. At which of the following points is the speed of the baseball a maximum? The key words here are speed, so I don't care whether it's rising or falling. And the other keyword is maximum. So when is it greatest? Here's what I know about a parabolic path. As the object rises up, it's slowing down. So the maximum from the beginning would be as soon as it left the person's hand, which ideally would be A. Because of symmetry, I know that the speed at A is going to match the speed at C. And anything above those 2 points is going to be slower. So I have this outlier point D. I know at the peak it's 0. So from 0 all the way to D, it's had time to accelerate, which means the speed at D is going to be greatest. If that does not make too much sense, here's another way to think about it. Let's say it was thrown upwards at 10 meters per second. Well, it's going to get to 0 at the peak. And then at point C, it's going to reach 10. Well, what do you think is going to come from C to D? It's not going to get slower as it falls down. That's why letter D is the only option here that makes sense. Number 3 reads, a machine launches a tennis ball at an angle of 25 degrees above the horizontal. The ball returns to ground level. Which changes would necessarily decrease the time the ball is in the air? So let's picture this really quickly. I have something launched into the air, 25-degree angle at some speed v. So the part here that affects the time the ball's in the air is the vertical component of the velocity, this vy. The greater the vy is, the more time I spend in the air. So there's 2 ways I can decrease vy. I either, 1, decrease the angle, so I'm going to decrease theta, or I can decrease the speed, in this case v. So I'm going to be looking for answer choices that follow this line of reasoning. A, decrease the launch angle, that's a great idea, and increase the ball's initial speed. Well, this is sort of a bit of a mystery. In order for us to answer fully, we'd need to know it by exactly how much. But what I can get from this is that if I decrease the launch angle, yes, the time the ball's in the air is going to decrease. But if I also increase the ball's speed, I make that Vy larger again. So it's as if I made no change at all. So A cannot be our answer. Letter B, increase the launch angle. Well, that's going to increase the Vy, which increases the time. but at the same time, you're going to decrease the ball's initial speed. So this performs an increase in time and then a decrease in time. And I'm essentially getting back to this scenario right here, where there's essentially no meaningful net change. Letter C, increase the launch angle, that's going to increase time, and keep the ball's initial speed the same. Well, essentially all that I'm doing is I'm just increasing the speed. Whereas A and B, there is essentially no change. So C cannot be our answer. I'm left with letter D, but let's make sure that it makes sense. Decrease the launch angle, yes, that's going to decrease the Vy, and keep the ball's initial speed the same. That is perfect. Number 4, during football practice, a football is kicked with a speed of 22 meters per second at an angle of 60 degrees above the ground. At that instant, an observer rides past the football in a car that moves with a constant speed of 11 meters per second in the same horizontal direction that the football travels. According to the observer in the car, the ball will, and I have 4 different options here. So let's visualize this. This football is kicked at a speed of 22 and an angle of 60 degrees. I also have a car moving alongside it that's traveling at a rate of 11 meters per second. Well, we're trying to put ourselves in the frame of reference of the car and understand what a person in the car would describe the motion of the football as. Well, we can determine how fast horizontally this football is going by finding our x component of the velocity. And that's going to be 22 cosine of 60. In your calculators, that's going to give us 11 meters per second as well. Since both the football and the car have the exact same horizontal velocity, then to the observer's eye in the car, the football is not going to appear to be moving left or right, but rather it is only going to appear to be moving up and down. This scenario where they are both moving at the same speed is the same as if you sitting down in a chair on the sofa, if you just toss up your phone into the air or a ball, toss it straight up, let it fall back in your hand, that is no different than what the person in the car is observing. Because you sitting on the sofa have a speed of 0. The ball in your hand also has a speed of 0. Because these two speeds match, the object appears to not be moving forward or backward. And that is the same thing as both the football and the car moving at the exact same horizontal velocity. Therefore, the observer will not see a parabolic path. The observer is just going to see a football going straight up and then straight down. Follow a path that is straight up and down in the y direction. That's exactly it. It's not going to follow a hyperbolic path in the x direction, and it's not going to follow a straight line that is angled with respect to the x direction. No. B would be our correct answer here. Number 5 reads, a projectile is launched with speed v at an angle 30 degrees above the horizontal. It travels a horizontal distance d before hitting the ground. Suppose the projectile had instead been launched at the same speed, which is v, but at an angle of 60 degrees above the horizontal. What would the new horizontal distance traveled by the projectile be? So we're trying to compare ranges here. Now, if you're aware, we can immediately take advantage of an idea of complementary angles. The concept is that if you launch an object at one angle, let's say 30 degrees, and then you launch the angle at its complementary angle, this just means theta 1 plus theta 2 will need to be equal to 90 degrees. If you meet this condition, then the ranges are equal. Because 30 and 60 degrees do equal to 90 degrees, then my range is going to be the exact same, and that will be letter C. Now, if you are unaware of this concept and you were going to solve this mathematically, here's how you would do that. Let's picture the motion of this object. It's launched with speed v at an angle above. It's going to travel a horizontal distance d before hitting the ground again. So from here to here is a distance d. The question is asking about this new horizontal distance given a different angle measure. Because the object returns to the original height from which it was launched, then I can take advantage of this range equation for a projectile, where the range is equal to v squared sine 2 theta over g. Now, since I have essentially no numbers, what I'm going to do is that I'm going to find the ratio r prime over r and see what that value is. If it's greater than 1, then the range is going to increase, and we'll determine by what number that is. If the ratio is evaluated to be less than 1, then the range is going to decrease. But if that ratio is 1, which I expect, then the range is going to be the exact same. So r prime is going to represent the range given a certain change to the initial conditions. The only change that there is a change to the launch angle. So let's see how we write that. This is going to be v squared times sine of 2 times 60 divided by g. This is my prime version. This is my changed version. Next, I'm going to write my original r in the denominator, which is going to be v squared sine of 2 times, in this case, it's 30 degrees. That's the original angle divided by g. Now, I have a complex looking fraction here, but all that I'm going to do, this in black that I'm just drawing over, is my real division sign. So this is the numerator, this is the denominator. So what I'm going to do is that I'm going to multiply by the reciprocal of the denominator. So I'm going to multiply by g over v squared sine of 2 times 30. And that will allow me to eliminate this real denominator part. So instead of doing division, I'm going to be performing multiplication. And what we see happen is that my g's will cancel, my v squareds will cancel. The ratio r prime over r is going to be equal to the sine of 120 over the sine of 60. In your calculators, if you perform the sine of 120 over sine of 60, that is going to be a ratio of 1, which I expected. So when I multiply the r on both sides, what I'm going to get is that r prime is equal to r. That means that the new horizontal distance is the exact same as the original one, a distance d. So let me erase this part real quick, so that way I can select my answer choice, letter C. So that is how you would solve this problem using mathematics instead of the concept of complementary angles and the ranges for projectiles. Number 6 says at t equals 0, a paintball is shot out of a paintball gun horizontally off a 1,000 meter tall cliff. At the same time, a paintball is released from rest, dropped from the same height. Ignoring air resistance, which paintball strikes the ground with a higher speed? So I have two scenarios here. One is dropped, and the other is shot out horizontally. Now, we want to know which one of these two is going to hit the ground with the higher speed. Now, for the dropped one only has one component of velocity, and that's a vertical velocity that is being increased by gravity. The one that is shot has the exact same Vy as the dropped one, but it also has a Vx because it is shot horizontally. So if I were to draw these as vectors, the dropped one is going to look like this. That's the Vy. But the other one, the shot one, has a horizontal and then a vertical one. So the actual speed is described by the resultant, which is going to be found using the Pythagorean theorem. And so this speed v must be greater than just a single vertical velocity, because this one has the exact same vertical velocity downward, but it also has, in addition to it, Vx. So I am adding to it in order to find this hypotenuse v by following the Pythagorean theorem. So my answer will be letter A, the paintball shot from the gun. Not the one from rest, that's only Vy. Both paintballs hit the ground with the same speed? No. And the answer depends on the initial velocity? No. Coming into number 7, the actual answer for this question is not on A, B, C, or D. So there is an error in this question with the answer choices, but let's go ahead and solve it. 7 reads, a football is aimed at a target on the wall, a distance L away from the throwing position, from which the football is launched horizontally. So here see the football, the distance L right here. Because of gravity, the bullet strikes the wall, a distance delta y below the mark, as suggested in the figure. I assume that by this bullet, we're talking about the football. Here's the question. If the distance L was half as large and the football had 4 times the initial velocity, how would delta y be affected? Typically, when we're doing problems like this, where there's no numbers and we're trying to see what happens when we change one variable or when we change the initial conditions, typically we're only modifying one value. But there's no rule or law that says you can only modify one value at a time. Here we are modifying 2 values. In order to solve this, we solve it like any other standard kinematic problem, where we have our picture already drawn for us, but what we're going to do is we're going to identify the knowns and unknowns, and we're going to find a relationship that connects all the ideas together. I know that my AY is equal to negative G. I know that the horizontal displacement is equal to L. My initial horizontal velocity, we're just going to call that V. I know that there is a vertical displacement, and well, there's no other special symbol for it. It's just delta Y. And what I'm looking for is how this delta Y changes. How does it change when we make these two adjustments? Whereas where L is half and V is 4 times greater. So here we have a projectile. And so we need an equation that connects both the horizontal distance traveled as well as the vertical distance traveled. The only variable that is in common with the horizontal and the vertical motion is time. So let's analyze our horizontal equations. So in the horizontal direction for a projectile, we only have one equation, where the final position equals to the initial position plus the initial horizontal velocity times the time. I'm going to define the beginning to be 0. So I'm just going to get that the final position is equal to the initial horizontal velocity times the time. So I'm going to create an expression using this information for the time. So I'm going to divide the velocity across, and I'm going to find that the time that it takes for the object to hit the target or to hit the wall is xf, which is the same thing as L, over the horizontal velocity, which is just v. This relationship is important because it connects the time with the horizontal motion. Because I'm looking for how the delta y changes, I'm going to substitute this into a kinematic equation of constant acceleration. Given that I have ay, I now have time, I need to have a delta y, and I can confidently say that the initial vertical velocity of the football is 0. So given all that information, I'm going to use this equation. So here, my vyi is 0, so this entire term is going to cancel. In my next step, I'm going to rewrite what I have here, but at the same time, I'm going to substitute L over v for my delta t term right here. So I'm going to get delta y equals negative 1/2 g times L over v squared. What I'm going to get is L squared negative L squared g in the numerator, and I'm going to bring the 2 to the denominator, 2v squared. This is the relationship between my vertical displacement, the horizontal length that the football travels, and then the horizontal speed that it is launched with, its initial velocity. So in order for me to find how this delta y changes, I need to find the ratio delta y prime over delta y. So remember, my delta y prime is going to take all my changes into consideration. What I'm doing is that my distance L was half as large. So I'm looking for half L and 4 times the initial velocity, 4v. That's what I'm going to plug in for L and for v. So in my delta y prime, I'm going to have, let's see the equation, half L squared times g divided by 2 times 4v squared. So together I have accounted for this decrease in the length by half, and I have accounted for the increase in the initial velocity by a factor of 4. I then need to divide this by the original delta y, which is just L squared g over 2v squared. So I removed the negative sign just because I'm going to have a negative on the top and then a negative on the bottom, and they're going to cancel out anyways, so I just did not bother to write it. So to simplify complex division, we're going to perform multiplication instead, and I'm going to multiply by the reciprocal of the denominator. So I'm going to multiply by 2v squared over L squared g. I'm going to rewrite this ratio here, delta y prime over delta y is going to be equal to, well, so now I can forget this. I have 2's that cancel out, I have g's that cancel out, and let me expand everything that's being squared in this next step, so that way we can see exactly what happens. So half of L squared, that's half L times half L. Half times half is a fourth. L times L is L squared. So that's what I'm going to get in the numerator there. 1/4 L squared. Coming across in the numerator up here, I have a v squared that is also left over. So it's 1/4 L squared times v squared divided by what's in the denominator, 4v to the power 2. So 4v times 4v is going to be 16v squared. So in the bottom, I'm going to get 16v squared, and I also have this L squared in the bottom. So this was the 16v squared. This is the L squared that's left over. So I have accounted for everything. Now let's see what cancels. L squared, v squared cancels. The ratio I'm left over with is a fourth divided by 16. I can go ahead and bring this 16 up and multiply together. I'm going to get 1/64. So the ratio delta y prime over delta y is equal to 1/64. So if I multiply both sides by delta y, I'm going to find that this new vertical displacement is going to be 1/64 of the original displacement. Now, my answer choice is not there, so I will be creating that. Delta y will be 1/64 as large. I believe this is an error with the way the question is itself. I believe that if we did not account for 4 times the initial velocity, you would get one of these original answers of A, B, C, and D. But I think there was just an error in the way that this problem was constructed to begin with. Number 8 reads, a ball is kicked from the ground with an initial speed v at an angle, not g, but it should be theta, above the horizontal. Which of the following best describes the magnitudes of the velocity and acceleration of the ball when it reaches the highest point in its trajectory? So we have something launched at some angle theta. It's going to follow our parabolic path. At the very peak, I definitely know that my acceleration, the magnitude, is equal to g, but the direction is always downward. So I can cancel out C and D. At the peak, the velocity is 0 vertically, but it still has a horizontal piece to it that remains constant throughout the entire trajectory. And so if I have something launched at speed v at an angle theta, the horizontal component would be v cosine theta. So that will be the amount, and my answer is letter B. Next, we're going to dive into the free response questions. Number 9 reads, in order to escape an impending physics, whatever that means, Anderson escapes in a boat across a river of width W equals 300 meters, as shown. The river has a current flowing to the east at a speed of 6 meters per second. When Anderson reaches the other side of the river at point B, he has drifted 180 meters downstream from point A. How fast does Anderson paddle the boat relative to still water? So I know the separation here is 180 meters. I know the vertical one is 300 meters. So we're looking for how fast our friend can paddle on his own. But we know that the current is pulling him towards the right. So we can analyze his motion horizontally and vertically. So I know that vertically, our friend was displaced positive 300 meters. Horizontally, our friend was displaced 180 meters. I know that the velocity of the boat horizontally is going to be 6 meters per second. What I'm looking for is the vertical speed of this motion, which describes how fast he can paddle. That's what I'm looking for. What I can do in the horizontal is that I can find how much time has passed by the time Anderson reaches point B. And why that's so important is that that's going to be the exact same time over here in the vertical. And that's going to allow me to solve for Vy, how fast Anderson can paddle this boat. So to find the time here, it'll be my displacement divided by my speed. And that's going to be 30 seconds. So it's going to take Anderson 30 seconds to reach point B. So I can use that my velocity will be equal to my displacement, will be delta y over the time, or you can think of it as just speed equals distance over time. So the distance traveled vertically is 300 meters. The time it takes is 30 seconds. And so Anderson by himself can paddle at a rate of 10 meters per second. Part B says, Sebastian pilots the 1,000 Sunny across the ocean in his quest to be king of the pirates. He pilots the boat with a velocity of 50 meters per second, 45 degrees south of west as shown. There is a strong ocean current pushing on his boat that is in a direction 30 degrees north of west as shown. What is the resultant velocity of Sebastian's boat? So this problem is just a basic vector addition problem, but except just applied to velocities. I know that to find my resultant velocity, it's just the vector sum of the components of that resultant vector. I know that I can find my resultant component for x and y when I just add the individual components. So I'm going to label this as vector A and this one vector B. So all I have to do is add AX and BX, and that's going to give me my RX. And then I can similarly find AY and BY and then build my resultant vector this way. So my final answer is going to have a magnitude and a direction. So let's go ahead and deal with vector A. Here's my vector A. I have a horizontal piece that comes this way. This is AX, and I have a vertical piece that comes down. This is AY. Now, because the angle measure is towards the left or right, AX is going to be A cosine theta. But because it points towards the left, it's going to be negative. Same thing for the Y. It's going to point down, so it's going to be negative A sine theta. So let's quickly perform that math. AX is going to be negative 50 meters per second multiplied by the cosine of 45. AY is going to be negative 50 meters per second multiplied by the sine of 45. For both of these, I'm going to get negative 35.4 meters per second. Just a quick note, if you have a 45-degree angle, that's what shares these components equally. So whenever you have 45 degrees, your x and y components will be equal, and this shows you that. Now let's find bx and by. Now this vector is drawn a little bit funny, but I have a vertical piece that comes up, and then I have a horizontal piece that comes leftward. So this would be my by, which is positive, and then my bx, which is going to be negative. Again, since my angle measure is towards the left or right, my bx is going to get cosine, so it's going to be b cosine theta, and then my by is going to be b sine theta. So bx is going to be negative 12 meters per second multiplied by the cosine of 30, and my by is going to be positive 12 meters per second multiplied by the sine of 30. So for bx, I am going to get negative 10.4 meters per second. And then for by, I'm going to get positive 6 meters per second. I'm going to use all four of these values in order to build my Rx and my Ry. So Rx is going to be negative 35.4 meters per second minus 10.4 meters per second. I'm going to shift this one up a little bit. Altogether, my Rx is going to be negative 45.4 meters per second. Now for Ry, I'm going to add up all my y components. Ay is the same, negative 35.4 meters per second. But this time I'm adding by, so it's going to be plus 6 meters per second. That's going to give me negative 29.4 meters per second. Now that I know the value, the magnitudes of the components, I can build my resultant velocity vector. I know that in the x direction, if I start from here, I'm going to go negative 45 horizontally. So it goes left, negative 45.4. And then it also goes downward, negative 29.4 meters per second. So the resultant velocity is going to be this one, the vector sum. I'll call it V, or we can call it R, it doesn't matter. And the angle measure will be here. So to find the magnitude of this vector, I'm going to do the Pythagorean theorem. The square root of negative 29.4 meters per second squared plus negative 45.4 meters per second squared. Leave this for your calculator. It's going to output 54.1 meters per second. So that is the magnitude. That is how quickly this boat is moving at a rate of 54.1 meters per second. Now, in what direction is it moving in? Well, I can find the angle by computing the inverse tangent of opposite, that is 29.4, divided by the adjacent, which is 45.4. By keeping these values positive, I'm going to find an angle measure that is just incorporated in this triangle here. So I'm not allowing for any negatives or anything like that. But what I have to do, because I keep it positive, is that I need to interpret it correctly, setting my beginning as the origin, where this is east, north, west, and south. So this angle measure is going to tell me how much in between west and south I'm actually traveling in. So my angle measure, when I put into the calculator, is going to give me about 33 degrees. Altogether, my final answer is going to look like this. We can call this the velocity of the boat, which means I can call it VB. You can give it any name that you want. But the velocity of this boat is going to be equal to a magnitude of 54.1 meters per second at a direction of 33 degrees. Now, I first started towards the left. That's west. So I have blank of blank. Wherever you begin, that's the second letter. So I'm going to start west, and then my vector tilted this way towards the direction of south, and that will be the first blank. Wherever you're headed towards is always the first blank. Wherever you start is going to be the second blank. So altogether, the velocity of this boat is 54.1 meters per second, 33 degrees south of west. Because from west, my initial part here, I had this amount of degrees to get this resultant vector, but it is in the direction of the south direction. So 33 degrees south of west. And that completes part B. Next, number 10. An airplane flies at a velocity of 220 meters per second directly east over Palm Beach. Genevieve, a passenger on the airplane, runs toward the back of the airplane at 5 meters per second. At the same instant, Lauren drives directly west toward the airplane at a speed of 15 meters per second. Part A wants us to calculate Genevieve's velocity relative to Lauren, which is essentially meaning how fast Lauren is approaching Genevieve. So we have a lot happening in this problem. So it's very important that we draw an accurate pictorial representation of what's going on. So here's the ground. I have Lauren who's driving. This will be the positive x direction. So we're driving west. So Lauren is driving this way at a rate of 15 meters per second. There's a plane in the air and it's going east at a speed of 220 meters per second. Inside of the plane, we have Genevieve that is moving towards the left. She's running towards the back of the plane, which is obviously towards the left. And she does so at a rate of 5 meters per second. Now, this is a relative velocity question because the word relative comes out. So we need to be careful with how we label our velocities. And here's how we're going to do that. I know that the horizontal velocity of the plane relative to the ground, I'm going to write it in this fashion with a comma because I'm going to use the letter G multiple times for Genevieve and then for ground. So in order to avoid confusion, I'm going to write it like this with a comma. So that way we can be clear as to what we are talking about. So the velocity of the plane with respect to the ground or relative to the ground, that is 220 meters per second. Next, I know that the velocity of Lauren with respect to the ground is equal to negative 15 meters per second. But wait, it tells us her speed is 15. So what this means is that from the eyeballs of the ground, So if you're just standing on the ground, how do you perceive Lauren's motion? Well, she's going 15 meters per second to the left. So that's what L, ground represents. Now let's talk about Genevieve. The velocity of, I'm going to put Gen for Genevieve, relative to the plane is just -5 meters per second. The question wants us to calculate the velocity of Genevieve with relative to Lauren. So I know the structure of the relative velocity formula. So my first one needs to begin with Genevieve and I have my blank, plus this other speed that's going to have a blank and it must end with Lauren. And the inner two subscripts is typically our inertial reference frame. So the object in this scenario that is not moving at all would be the ground. So I'm going to put G. So I need to find the velocity of Genevieve relative to the ground. I'm going to add to that the velocity of the ground relative to Lauren. And that's going to give me the velocity of Genevieve with respect or relative to Lauren. Now, there's some funny business with this term right here. Let's explore it on the left-hand side. In order for me to find the velocity of Genevieve relative to the ground, I need to repeat the process actually once again. Genevieve with respect to the ground, well, my first one needs to begin with Genevieve with a blank plus this blank and need to have a G here for the ground. Well, there's something that connects these two where these G's represent ground, and what connects these two is actually the plane. So when I'm finding the velocity of Genevieve with respect to Lauren, what I'm actually finding for Gen, G is the velocity of Genevieve with respect to the plane. Well, I know what that is, -5 meters per second. And I'm adding to that the velocity of the plane with respect to the ground. Well, that's 220 meters per second. So here I'm going to get 215 meters per second for that. So I know what this is, 215 meters per second. And what I'm adding to that is the velocity of the ground relative to Lauren. So from Lauren's eyeballs in the car, how does she perceive the speed of the ground? So when she looks at the ground, it's going to look as though the ground is moving towards the right. And so it looks like when you look at the window, it looks like all the road is moving behind her. And so we also know that I have L ground. And whenever you flip the subscripts, because here I have ground and then L, I'm just going to negate the velocity. So it's going to be a positive 15 meters per second. So to answer the question, the velocity of Genevieve with respect to Lauren is going to be equal to 230 meters per second. To think about this intuitively, on the plane, considering only Genevieve and the plane, there's a velocity this way at 215. And then here I have Lauren moving to the left with 15. Because they're getting closer to each other, they appear to be faster. So those velocities combine in the way that I've shown you here using the relative velocity formula to give us 230 meters per second. Part B says, Genevieve drops a Hello Kitty plushie directly down out of the airplane. Lynn stands at rest on the ground and watches this all go down. Describe the path and calculate the speed of the plushie after falling for 3 seconds according to Genevieve and Lynn. So Genevieve is on the plane and she is the one dropping an object straight down. So both the object and Genevieve have the same horizontal velocity of the plane. So they're not going to perceive that. So what Genevieve is going to see is just that the plushie will fall straight down. So that's what Genevieve is going to see. Just like you sitting down in your sofa or your bed or your desk and you just drop an object, that's exactly what Genevieve is going to see as well. So now we need to calculate the speed. So let's create some knowns and unknowns here. I know that the acceleration is -g. This delta t that I'm interested in is 3 seconds later. I know that because it is dropped, my initial vertical velocity is 0. And I'm looking for the final speed. So given these knowns and unknowns, I'm going to use this formula. I know my VYI is 0, so my final velocity is going to be -9.8 meters per second squared, all multiplied by 3 seconds. So my VYF is going to be -29.4 meters per second. Since it's just asking me for speed, I don't care about the negatives. So the speed is just 29.4 meters per second. That would be how fast the plushie is falling after 3 seconds. Next, I'm going to calculate the same thing, but from the perspective of Lynn. So Lynn is standing at rest on the ground and watches everything. So I have this exact same scenario, but this time Lynn is standing on the ground. So Lynn is able to observe the ball with a velocity rightward. That's the exact same as a plane, and with the velocity that's provided by gravity. So what Lynn is going to see is a parabolic path. Now, I need to calculate the speed of the plushie from Lynn's perspective. Well, I need to be very careful. I need to take into account that this object from Lynn's perspective has a horizontal velocity that is the exact same as the plane, and that is 220 meters per second. So rightward, I have 220 meters per second, and downward, after 3 seconds, I know that it is negative 29.4 meters per second for its velocity. So this is Vx, this is Vy, and this total speed is going to be the resultant of this right triangle. So I'm just going to call it V, and let's solve for it. So V is just going to be the square root of Vx squared plus Vy squared. Plugging in my values, I'm going to get 220 meters per second squared plus negative 29.4 meters per second squared. All together, the calculator is going to give me a speed of 222 meters per second. And that is the speed that Lynn observes standing on the ground in this scenario. Moving on to number 11, it reads, Jano throws a basketball that goes directly into a net as shown. Jano throws the ball at V equals 8 meters per second at an angle of theta equals 60 degrees and at a release height of 2 meters as shown. The ball travels downward through the basket at a height of 4 meters. Part A, calculate how far away from the basketball Jano is when he throws the ball. So I'm looking for this distance, the distance between Jano and the hoop. So I'm looking for what that is. So what is this displacement? Let's go ahead and set up knowns and unknowns. I know that because this basketball is launched at an angle, my initial horizontal velocity, my Vxi is going to be 8 cosine of theta. My Vyi is going to be 8 sine of theta. Because it's in the air, my acceleration is negative g. The initial height from which it is launched is 2 meters, and the final height that it reaches when it touches the net is 2 meters. So I'm looking for this delta x, how far away is Jano, but what's going to help me out a ton is if I also know how much time it took to reach the net. And that's what I'm going to do first. Given everything that I have here, I'm going to use this equation. I'm going to plug in my numbers so that way we can see the quadratic formula come out. So my delta y is final minus initial. So right here, it should be 4 meters. So final minus initial is going to be 4 meters minus 2 meters. And that's going to be my Vyi. That is going to be 7. So 7t minus 4.9 t squared. So simplifying and moving everything over to the right format, I'm going to get negative 4.9 t squared plus 7t is minus 2. All of that's equal to 0. So for the quadratic formula, my a is equal to negative 4.9, my b is equal to 7, and my c is equal to negative 2. So I should get two values here for my time using the quadratic formula. The quadratic formula is negative b, so negative 7, plus or minus the square root of b squared, so 49, minus 4 times a, negative 4.9, times c, which is minus 2. And I'm going to divide everything by 2a, which is going to give me negative 9.8 back. When I simplify what's under the radical, I'm going to get that t equals negative 7 plus or minus the square root of 9.8, all divided by negative 9.8. Remember that the plus or minus is going to give me two solutions. So t1, I will just say that it is the plus version, and that t2 is going to be negative 7 minus the square root of 9.8 divided by negative 9.8. So t1 is going to give me 0.39 seconds, and t2 is going to give me 1.03 seconds. So which one is correct? I have two times for when my displacement is 2 meters. Because I begin 2 meters up the ground, and then when the ball is in the net, that happens 2 meters above the ground. But if you think about it, the ball is not traveling in a straight line. It's actually going in a parabolic shape that looks more like this. So what that means is that there is multiple times when the basketball is at 2 meters above where it was launched from this place. It does so here, and it does so right here. There are 2 times. If I can see, I also have 2 times. One is very early on. That would suggest that that is T1 right here. And the later time would suggest that that is T2. And I'm interested in when the ball is at this position. T2 is going to be the time I'm going to use to calculate how far Jano is away from the basketball net. The question of calculating how far away something is a horizontal one. And in the horizontal direction, I just have one equation. xf equals xi plus vxi times delta t. So I'm going to call my initial to be 0, and I'm looking for this final position. So my final position is going to be that initial horizontal velocity which is 8 cosine theta, 8 cosine of 60, multiplied by this time, 1.03 seconds. So I'm going to get a final position of 3.89 meters away. So that means J0 is 3.89 meters away from the basketball net. Part B wants me to calculate the maximum height reached by the basketball. Let's do some knowns and unknowns again. The basketball is in the air, so my acceleration is negative g. I know that at the maximum height, the vertical velocity is 0. I'm looking for this final height that's reached. And I know that it began 2 meters above the ground. And I also know how fast it was moving initially. That is 8 sine theta. Of course, where that theta is 60 degrees. We know what that is. So in order to calculate this, I'm going to use this equation. So here, I'm going to solve for my delta y because I know delta y is final minus initial, and I'm going to expand it once I have it solved for. So my VYF is going to be 0 because the peak is 0. I'm going to add the 2g delta y at the same time to the other side, and this is what I get from that. So I get 2g delta y equals 2 VYI squared. I'm going to divide it by 2g on both sides to isolate my delta y. So this is what I'm going to get. Next, I'm going to expand my delta y to be y final minus y initial equals VYI squared over 2g because I'm only looking for the YF. I don't need the YI. So I'm going to add it over to the other side. So all together, my final height, my maximum height is going to be the initial velocity squared over 2g plus that 2 meters that it began from. All together, I'm going to get 7 meters per second squared divided by 2 times 9.8 meters per second squared. All of that, we're going to add 2 meters to it. So my final height, or the maximum height reached, is going to be 4.5 meters. Now, before we move on to part C, we need to make one more quick calculation. So the ball is going to follow this path, and it's going to arrive at the net, which is 2 meters above where it was originally shot from. And that took 1.03 seconds from what we found. Then the very last sentence says, the ball travels downward through the basket at a height of 4 meters. So I need to find out how much time it takes for this basketball to fall this height of 4 meters. And I know that it's negative 2 delta y over g. So this time interval is just going to be 8 meters divided by 9.8 meters per second squared. And our calculator is going to give us a time interval of 0.9 seconds. That's going to be important for us later. When I add the 0.9 to 1.03, it is approximately 2 seconds. 2 total seconds that this ball takes to hit the floor. Now that we know that, let's move on to part C. Part C says, sketch the graphs of the displacement, velocity, and acceleration of the ball in the horizontal and vertical directions. Distinguish the graphs by having the x components be solid lines and the vertical components as dashed lines. Label any maxes and min. So for the x component, I know that acceleration is 0, so I'm going to treat that as a solid line for 0. For the y component, I know that the acceleration is constantly at negative 9.8. So I'm going to have a line like this that's at negative 9.8, and I'm just going to make it dashed. So that will cover my acceleration. I know that my x component has constant velocity, and that x component is 8 cosine 60. And 8 cosine of 60 is equivalent to 4 meters per second. So, and for my velocity, let me go by 2s, 2, 4, 6, 8. My x component is going to have a constant horizontal velocity of 4. Now my vertical velocity, it begins at 8 sine theta. 8 sine theta is about 7. 8 sine theta, which is 60. Remember, this was my VYI from when it was launched at. It's equal to 6.9, but I'm going to round that up to 7. So it's going to begin at 7, but because the vertical motion is affected by gravity, it's going to have a slope of negative 9.8. And I just assume that's a slope of negative 9.8. I'm not really drawing it too carefully. Lastly is my displacement graph. So for my horizontal motion, the object was only displaced starting from here, from 0 to 3.89 meters, approximately 4. So the displacement for the horizontal motion is just 4 meters approximately. So starting from 0, we can create a grid going by ones, 1, 2, 3, 4. And I'm also not being specific with the times either, just because I don't like the scaling of it. But I know it takes 1 second in order to reach this 4. I'm just going to call this line as being 1 second right here. This would represent the horizontal displacement of the basketball. Now what happens to the vertical displacement is that it begins, my yi is 2 meters, and then at the very end it's going to end up on the floor. Yf is 0. So my delta y is going to be -2. And it does that after a total of approximately 2 seconds as we calculated, because it's 1.03 seconds that we got right here, and that's why we needed this extra calculation on the side, an additional 0.9 that we're going to round up to 2. So vertically, I counted, let's do 1, 2, 3, 4, 5, 6. So another 1, 2, 3, 4, 5, and 6. This is 2 seconds. And for the vertical motion, we actually traveled 2 meters down. So here's what I know. I know that the final position 2 seconds later is at -2 meters when it hits the floor. But at the peak, at around 1.003 seconds, it reaches a max height of 4.5 meters, somewhere about up here. And I know as soon as the basketball is launched into the air, it's slowing down. So it's going to have a curved line. So here's what I know about the displacement of the ball for the vertical motion. It begins 2 meters above the ground, and then it's being tossed up and it's going to slow down, reaching its max height, and then it is going to decrease in position past its original height and then accelerate towards a displacement of -2. And let's make this black line dashed the way that it asked us to. Let's move on to the last example. Number 12 reads, an airplane is flying 1,200 meters above the ground at a speed of 200 meters per second. It drops a pumpkin on a target on the ground. Part A wants us to calculate how far from the target the pumpkin must be dropped so that it lands on the target. So if we need to know how far away we need to be to release a pumpkin, we need to find what that range is. So let's create some knowns and unknowns. I know that the vertical acceleration is -g. I know that the initial vertical velocity is 0 because it states that we drop a pumpkin. I know that the initial horizontal velocity, or actually the horizontal velocity throughout the entire motion, is 200 meters per second. And I'm looking for this xf. How far away is it going to land? So that way I know how far away we need to be in order to drop the pumpkin so that it lands on the target. But in order to do this, we're going to need to also know the time of flight. Now, in order to find the time of flight for any projectile, you just need to know the vertical displacement. And we actually do know what that is. It's -1,200 meters. And the formula is -2 delta y over g. So it's -2 times -1,200 meters divided by g. So my time of flight is going to be 15.6 seconds. Now I'm going to use this time for the horizontal equation of motion, which is just the final horizontal position equal to the initial plus the horizontal velocity times the time interval. I always assume that my initial horizontal position is 0 because it makes things easier. And my final horizontal position is just going to be my horizontal velocity, which is 200 meters per second, multiplied by this time interval I just found, 15.6 seconds. So how far away that we need to be? We need to be 3,130 meters away in order for the pumpkin to hit the ground at the target. So we're flying in the plane, and as soon as we are this distance away from the target, we must drop the pumpkin in order for the pumpkin to reach the target. Part B says, calculate the angle the pumpkin's trajectory makes with the ground when it strikes. Now we saw another example similar to this, but we need to realize that the speed of the pumpkin has two components to it. It has the horizontal, which is constant, and it is the exact same as a plane, 200, and it has a vertical one. But we need to find out what that final velocity is, or what that final speed is for this pumpkin. Given everything that we know, I can use this equation. So VYF equals VYI minus G delta T. I know the initial vertical is 0, so my final velocity is going to be -9.8 meters per second squared multiplied by the time, 15.6 seconds. So my final vertical velocity when it hits the ground is -152.88 meters per second. And that's what belongs here, 152.88. What it's only asking us for is the angle. So because I know my opposite and my adjacent, then I'm going to do inverse tangent of my opposite over the adjacent. So my angle measure is going to be inverse tangent of 152.88 divided by 200. That's going to give me an angle measure of 37.4 degrees. Now I need to orient it correctly. My starting point is always going to act as my origin. This is east, north, south, and west. So I begin in the direction of east. That's the way that I drew my first vector. And then my second vector was drawn down. So I'm headed from the east. I'm going towards the direction of the south. So therefore, my angle is 37.4 degrees south, because that's where I'm headed towards, of east. East goes last because that's where I began. So again, that is south of east. Part C reads, how would your answer to Part A change if the airplane were flying at a downward angle when dropping the pumpkin? Justify your answer qualitatively. An example answer would be, the target would be closer because the pumpkin would have an initial vertical velocity, which decreases the time of flight. An additional detail to add would be that a decrease in the time of flight would also decrease that range, the horizontal range of the pumpkin. Part D says, suppose that instead of dropping the pumpkin, the pilot throws the pumpkin downward with an initial downward speed. Steve, the student, claims, since the pumpkin is given an initial vertical velocity, it will hit the ground with a greater speed. Since the pumpkin is traveling faster, it will also travel further in the x direction before hitting the ground. The first part wants us to evaluate which part of the student's reasoning is correct and justify it. Part 2 wants us to figure out which part of the student's reasoning is incorrect to justify our answer. So for part 1, this would be a sample answer. The student is correct in that a pumpkin that's given an initial vertical velocity will hit the ground with a greater speed because the pumpkin will accelerate at 9.8 meters per second squared on top of its initial velocity. In the last part, what part of the student's reasoning is incorrect? An example response would be, the student is incorrect in that the pumpkin will travel further in the x direction. Given an initial vertical velocity, the pumpkin's time of flight would decrease. Therefore, the horizontal range also decreases. And this will wrap up practice test number 2 for test number 1. That covers unit 1 of AP Physics. Thank you for sticking along this far into the video. I know we covered a lot, but I hope that these problems help you understand the concepts of 2D motion in a deeper level. Thank you for being a part of the College Physics series. I look forward to seeing you in the next lesson.